Okay, this video is going to walk you through a second example on how to do some curve analysis. So, reminder that we're looking for four things when we're trying to connect what my first and second derivative tells me about my function. We're going to try to determine intervals on which the function is increasing, decreasing, relative extrema, intervals on which the function is concave up, concave down, and then finally points of inflection. So today's example is going to be a rational function. And I'll be honest, I don't know exactly what this looks like. I have an idea because I've seen a lot of rational functions, but to try to sketch it right now, I really wouldn't have much of a clue of what's going on. So we're going to go ahead and start by using our second derivative, or sorry, our first derivative. So I am going to have to do quotient rule. There's no avoiding it this time. So denominator times derivative of the numerator minus numerator times derivative of the denominator all over the denominator squared. Make sure you're using parentheses so you don't end up getting into trouble here with the derivative. And I'm just going to see what I can do to tidy this up. Numerator is x squared minus 36 minus 2x squared. I'm not going to multiply out the denominator. I'm going to try to avoid that as much as possible. It looks like my numerator is giving me x squared minus 2x squared is a negative x squared minus 36 all over x squared minus 36 squared. And I really want to cancel that, but I'm not able to. I can factor out a negative if I want, and I get x squared plus 36 over x squared minus 36 quantity squared. And that's a negative out front. So I think that's as good as I can do for my first derivative, and probably as good as I need to do. So reminder that we're trying to find intervals of increasing and decreasing. So I'm going to take that and I'm going to try to find the critical points. Would be where my function could possibly have a maximum or minimum, not necessarily, but could. So I'm going to find when my first derivative is either equal to 0 or undefined. So for the equal to 0 case, that would be me taking my numerator and setting it equal to 0. So I'm going to do that and say I've got negative quantity x squared plus 36 equal to 0 would give me critical points, or critical point. That gives me x squared plus 36 is equal to 0 divided by negative 1. X squared is equal to negative 36. And I have no real solutions there. So that one's not going to give me any critical points. So then I'm just going to move on and I'm going to say, okay, I can look at where my denominator is equal to 0. And that would be taking the x squared minus 36 quantity squared, setting that equal to 0. Now I'm finding where my derivative would be undefined, and those would be other critical points. So that's going to give me, take the square root of both sides, x squared minus 36 equals 0. So x squared equals 36, taking the square root of both sides, I get x equals plus or minus 6. Critical points of my first derivative. So I'm going to come back to this screen, but I'm going to go ahead and start my function analysis, my number line analysis, if you will. So I can start to kind of plot what this function is going to look like. So I have a negative 6 and a positive 6 so far for critical points. So I'm going to go ahead and throw those up here, leave some space in the middle, and I'm going to do my first derivative analysis is 0 at negative 6, 0 at positive 6, and now I'm going to check signs in the in-between part. So I'm going to have to go back to this screen. And maybe I'll just do it up here, see if I can fit it in here. So my test values for my first derivative, I'm really using this simplified function right here. I'm going to find my derivative when I'm lower than negative 6. So let's just do negative 7. Derivative when I'm in between negative 6 and positive 6. I always like 0 is usually an easy choice. And then I'm going to have to go positive 7. And again, I'm just looking for signs. So I do have a fraction here. Negative 7 squared is going to be positive 49 plus 36. So that's going to be positive numerator. And I've got a negative out front. So that's giving giving me a negative divided by, denominator is also going to be a positive because I've got that squared, so that's giving me a negative overall. Going on to 0, well, that's going to give me again, a 0, and here's going to give me a positive 36 with a negative out front. So I've got a negative divided by a positive, which is giving me a negative. And then the last one, 7, I'm still getting, basically the inside of the parentheses here is always positive, and so is this once I square it. So I'm getting a negative out front, and then, or mine's in the numerator. So I'm getting a negative again. Interesting. So we had potential critical points. Well, we had critical points, which were potential maximum minimums, and my sign is not changing. So let's go back to my function, and I'm just going to jot that down, that I just got negative derivative negative in this section and negative in that section, which means my function is decreasing, decreasing, and decreasing. Wow, what an interesting function. It could just be a line for all we know, except it is a rational function, and we know something about rational functions. So that keeps me going, and I'm intrigued to figure out what the curvature of this looks like. So in order to figure out the curvature, I need to look at the second derivative and the concavity. We did write this yesterday, and maybe you want to do that. Decreasing, decreasing, decreasing. I usually like to draw the arrows because that means more to me. Okay, I'm on to my second derivative. So that means that I'm going to attempt to take the derivative of this. So I'm going to go ahead and rewrite that. So I've got that in front of me. So that was my first derivative. This is just me rewriting so I can fit it on the screen here, was negative x squared plus 36 all over x squared minus 36 squared. Again, that's exactly what I had right up here. So let's go ahead and take the second derivative. Quotient rule again. Here we come. Come on, Smartboard. Okay, so second derivative. Denominator times derivative of the numerator, which is a negative out front times derivative of the, it's really just a constant multiple, negative 1 times derivative of my parentheses, which is 2x minus, so that's just all multiplied together, that's one term, minus numerator, which is a negative x squared plus 36 times derivative of the denominator, which is 2 times the quantity x squared minus 36 to the first times 2x. Hopefully you caught that was chain rule right there, that multiplying by the 2x is the derivative of that x squared. So you could have done this, and you could have made it with u squared, where u is x squared minus 36. So you've got 2u right here times derivative of u, which is 2x. Okay, denominator squared. I gotta remember I'm doing quotient rule here, and I've got to do it all over denominator squared, which is x squared minus 36 squared and squared again, because the original squared was there. Wow, that is a lovely derivative. I'm really hoping I can do something with this, but I also don't want to spend a ton of time simplifying. Let's at least multiply and see what we end up with a little bit. I'm not going to multiply out the binomial squared. I am going to go ahead and take the negative 2x out front times x squared minus 36 squared. This is going to change into plus a positive. I should do that in a different color. There we go. And then I've got 2 times 2 is 4x times x squared plus 36 times x squared minus 36. And again, I'm really not multiplying out too much, because if I'm going to simplify, it's going to be easier if it's in factored form. Squared is to the 4th power. So I'm noticing, I'm not sure if you're seeing this, if you stare at it for a minute, you should be seeing that we've got an x squared minus 36 here, and an x squared minus 36 here, and then 4x squared minus 36 here. X squareds minus 36 quantities. So I'm going to cancel one of them. So this one's gone. One of the two is gone there, and that's just a first power, and then this becomes the third power. And that might be all I can do, but I can now go ahead and multiply out. So I've got negative 2. I'm going to go ahead and multiply out right now. This part right here, because I can go ahead and multiply out the, since I don't have a squared power here, I just have a binomial times a monomial negative 2x. So I'm going to go ahead and multiply that out. So I'm going to end up with negative 2x cubed plus 2 times 36 is 72x. Plus, again, I'm going to go ahead and multiply this part here. So I multiply this, and now I'm multiplying the other. So I'm going to end up with 4x cubed plus 36 times 4 is 144x all over x squared minus 36 to the third power. And if I keep going, I'm getting close, guys. I know it seems like we're never going to get there. But I see some like terms that I can combine. So I'm seeing that I can combine the negative 2x cubed and the positive 4x cubed, and then I've got the x terms that I can combine as well. So let's go ahead and do that, and we're going to end up with positive 2x cubed plus 144 plus 72 is 216 over x squared minus 36 cubed. And the last thing I'm going to do is I might as well, if I can divide by, or if I can factor out anything in the numerator. Factors are good because then it's going to be easier to do my test values. So if I can factor out a 2x, I'm going to end up with x squared minus 108. I'm sorry, that's a plus 108. All over x squared minus 36 quantity cubed. And ladies and gentlemen, that is our second derivative in final form, or at least I'm going to call it final form. So where am I? Okay, I found my second derivative. Why did I care about second derivative? Second derivative tells me about the concavity or the curvature of the function. Specifically, when my second derivative is either equal to 0 or undefined, would be possible inflection points where my concavity is changing. So I'm now going to take that and set it equal to 0. So that means I'm going to take the numerator and set it equal to 0. 2x times x squared plus 108 equals 0. So that means x could equal 0, or x squared could equal negative 108. And then that becomes undefined, no real solutions. But I did get x equals 0 as a critical point of my second derivative. And now I'm going to take the denominator and set that equal to 0, which is technically finding where my second derivative is undefined because I have a rational function. So taking the cube root of both sides, x squared minus 36 equals 0 gives me x squared equals 36, and surprise, I'm ending up with x equals plus or minus 6. That looks familiar. So critical points that were critical points in my original derivative, and then I've got this new one, the 0. So back to my number line analysis, second derivative we just figured out is 0 at negative 6. That was a lot of work to figure that out. It's also 0 at positive 6, and at 0, I'm going to have to add something here. At 0, it is also 0. So I've got 3 places, which means I actually have 4 intervals. I need to check in each of the 4 intervals to see what the sign of my second derivative is. So, time to do some more test values. Get ready to do some mental math. Here we go. So we need to be able to see our second derivative, which would be, I need a bigger smartboard. Okay, so I'm using this second derivative right up here, and I'm going to be doing, I'm going to be doing some test values for that. So let's see if we can move this. Okay. So test values. I'm going to find the second derivative at, let's just go -7 again. That worked last time. Let's go somewhere between -7 and 0. So I'm going to do -1 since I can't do 0 this time. Somewhere between 0 and +7 would be, I'm picking 1. And then, sorry, between 0 and 6. 6 is my critical point. So those are my 4 test values. So if I'm doing -7, I'm doing -7 times 2 is a -14. So I have a negative times -7 squared, that becomes positive. That whole thing is positive. So negative times positive divided by -7 squared is 49 minus 36 is a positive, cubed is a positive, which gives me a negative overall. Okay, and that's a little bit tricky, but certainly easier than doing the actual calculations. So let's do it again for -1. So for -1, I'm still getting a negative out front there. -1 squared is positive. I'm still getting positive in the other part of my numerator. And then my denominator, -1 squared is +1, but subtract 36, I'm getting a -35. If this quantity is negative and I'm cubing it, I'm going to end up with a negative down there, which gives me a negative divided by a negative, which is a positive. Okay, we've only got 2 left. We're getting there. So I'm plugging in 1. 2 times 1. Now I've got a positive out front. And then I've got 1 squared. That's still positive. So I'm seeing that that last term is always positive. I don't know if anybody else is seeing that. So I'm actually going to go ahead and do the other one while I'm at it. The denominator is 1 squared minus 36. Again, that's a negative, similar to the one above, because I'm getting -35 cubed. Negative cubed is a negative. So I'm getting a negative overall because I have a positive divided by a negative. And the last one there, any guesses? Let's see, I've got 7 squared is 49 minus 36. I'm getting a positive in the denominator. Cubing that gives me a positive for a positive overall. So, switching to my other screen in just a second, I've got negative, positive for my 4 intervals that I need to record on my number line. So I've got negative, positive, and most importantly, that's telling me about my concavity. It's concave down, concave up, concave down, concave up. And if we start to put that together with what I have above, concave down, remember, is not going to hold water. Concave down is something like this. And concave up is going to be something like this. So I'm decreasing, that's concave up. Concave down is going to be something like that. And then concave up for my last section. Obviously, I'm not putting these in a specific order, but in terms of where they would be on the y-axis, but that's giving me my curves. And if we think about what we know about rational functions, we do actually have an asymptote on both of these spots. And you should be getting a pretty good picture. I think that this is going to be connected. Let's go ahead and grab our graphing calculators and check our work and see how we did. And then we should write up our actual answers. So let's go ahead and graph, and then we'll write up what our intervals would be. So I just happen to have graphed this. Function was x divided by x squared minus 36. And there we have our beautiful graph. And you can see that concavity, concave up, concave down, up, down at the beginning there. And it is decreasing the whole way. So it looks like we did pretty good. If you were to write out your function or write out your answers to my original 4 questions. Original 4 questions were A, intervals of increasing. So increasing, we'll go with that first. Increasing, well, never. Decreasing on the interval -infinity to infinity. We're not going to worry about the asymptotes, even though it's technically not there. We're just going to go with, in general, decreasing for the whole function. B is relative extrema. That would be maxes and mins. There aren't any. C would be concave up. 0 to infinity, concave down. sorry, my bad. Concave up, I gotta look at my picture. Concave up was from -6 to 0, and then from 0 to infinity. -6 to 0, and 0 to infinity, and then concave down on -infinity to -6, and I think I messed that up again. Sorry, that was from +6. You really got to look at what you're doing here. I'm definitely screwing this up. From 6 is this spot. So this is 6 right here for the concave up, 6 to infinity, and -6 to 0. So if I fix that, -6 to 0, and this should be a 6 to infinity. Sorry about that. And then concave down on -infinity to -6, and 0 to 6. So it's concave down, basically concave down, concave up, concave down, and then concave up if you jump between intervals. Last question was points of inflection. And that would be where you had changes in concavity. So points of inflection would be, it has to be where your second derivative is either equal to 0 or undefined. And I'm also noticing, sorry, I'm making lots of mistakes today, that I didn't do this exactly right. My -6 and +6, if we go back to our work here, -6 and +6, maybe some of you already caught this. -6 and +6 came from setting my denominator equal to 0. So it is still a critical point, but that would be when my function, my derivative is undefined, not when it's equal to 0. So I should have put, I like to note in my curve analysis here, I like to note that by putting undefined for these places instead of putting 0. So again, my apologies. Okay, but regardless, sorry, point of inflection would be where your derivative is either undefined or 0 and changes signs. So that would be, point of inflection would be, since it's changing sign, my second derivative is changing sign between here and here, right at this, x equals -6. It's also changing signs here at x equals 0, and it's changing signs at x equals 6. So putting that on here, x equals -6, 0, and +6. Oh, that was quite a problem. Hopefully you were able to follow that and maybe even catch some of my mistakes as I made them. I think you should be pretty good to try some of the homework problems now. There are some relatively simple ones in terms of polynomials, and then I think I did give you a rational function to try and maybe a couple others. So good luck, take your time. It's easy to make mistakes, but just be careful with your work and you will be just fine.